Hello and welcome back to Corks and Quarter Notes. Tyler and I are back with our conversations about science, philosophy, and music. Today we begin the first of many conversations diving into astronomy. As always, if you enjoy the conversation, you can show your support by subscribing or following on your preferred podcast platform. So, we wanted to do an episode about astrophysics, but that was already seeming to be a bit too big of a topic for one episode. So we're thinking we're going to do multiple episodes, and where should we start at?
I was thinking that we could just start with looking at a stellar object, aka the sun.
The solar part of the solar system.
Mm-hmm. Where most of the mass is, gives us all the energy.
Yeah. Okay, well, we always like starting with defining what is the sun.
I'm going to say some technical terms, but we can break apart what they mean. The sun is a main sequence star, about halfway through its main sequence life. Pretty average star for the most part, if we look at our HR diagram, which shows kind of the distribution of where stars lay based on how bright they are and their temperature. Most stars lay in a band that goes from the top left to the bottom right. Our sun will be like right in the center of that band that goes across the screen, right in the yellow spectrum. So almost dead center of the HR diagram.
So of all the stars we look up, we see all those little points of light and such. In this graph that you're showing me, this is sort of a graph of the luminosity of all of those stars, and the sun's kind of in the middle.
Yes. So as you go up the graph, the stars are more luminous, so that the stars at the very top are very luminous and the stars at the bottom are quite dim. As you go from left to right, you go from hot to cold. So the stars on the far left and up high are very bright and very hot. And then as you go down, they become less luminous. And then as you go right, they become cooler as well.
Back in the day, we used to think the sun was a special object, and then those little points of light were other objects. We gradually realized they're the same sort of object. How do we go from just looking up, seeing the sun, seeing other stars, to knowing how hot the sun is and how luminous it is compared to those other stars?
So that's a tricky question. So the luminosity of our sun is pretty easy to get a number for, right? Because it's right next to us, so we can get what we'd say an absolute magnitude of it, like it's what it's actually how bright it is emitting. And the best we can do for stars that are far away is say what their apparent magnitude is, and that's just like what it appears to be to us,
like how far away it seems to be.
So objects further away are dimmer.
Right, like the sun and the moon look pretty close in size and brightness, even though the sun's
the sun is
away.
way brighter, but about the similar size in the sky, right?
Right.
But we know the sun is way further away than the moon. There are issues of how do you know if it's a very bright star that is really far away, or if it's more of a dim star and a little bit closer, they might appear as the same like apparent magnitude in the sky. So we have to build what we call like a distance ladder, and a way to measure the very closest of stars. We use what's called parallax. To think of a demonstration of parallax is to put your thumb just in front of you and then close one eye and then close the other eye, and you'll see on the background kind of jumps, and it kind of jumps between two. So what we can do is we can take a picture of a star. We'll look at a spot in the sky and take a picture of a star. Wait 6 months so we're on the other side of the sun. Take another picture, and the star will appear to bounce in reference to its background.
Right. Okay. Yeah.
And so from that, we get and that's only good for pretty close stars, because the angle becomes too small for us to measure. Like that little jump, the jump is almost immeasurable, or is immeasurable after a certain distance, right? once you just get too far. And so we kind of build a sphere around us of like known distances of stars. And since we know the distance of these stars and we know their apparent magnitude, how bright they appear to be to us, we can figure out actually how their overall magnitude, like how bright it actually is, because we know the relationship between how far it is and how bright it appears. And so from that, we figure out how bright the actual star is. And then we have this whole like library of, we have some bigger stars and then they have these kind of properties. And then we kind of just like take that and we just build outwards. And then we say, oh, well, this star looks like this one that's really close to us. If it is that kind of star, it must be this far away. And then you just kind of build out from that.
I see. Very interesting. The sun is an average star.
Yeah, it's pretty much dead center of the HR diagram.
I guess the next question would be, what is the sun made of? Because I mean we've gone through a lot of different ideas. We used to think it was a god.
Right.
And we move forward and we thought it was a burning coal rock, but what is it? And how do we know?
Well, we know that it's made mostly of hydrogen and has a small amount of helium and then trace amounts of larger elements. The initial problem is coming up for an account of why it's so bright. There has to be some sort of fuel for the energy that it's emitting. And we've proposed, like you said, coal perhaps. And then we know you can take like a kilogram of coal, ignite it, see how long it burns. And then if you extrapolate that to the sun and say, what if the sun was coal? We know about the size of the sun, so we can get how much mass that would be. And we could calculate how long that would burn. And it would be on the order of like hundreds of thousands or millions of years. And we know from fossil records and stuff of that sorts, there's no way that the sun is just a few million years old. So we need some other kind of fuel in order to create this outgoing energy that we feel whenever you go outside and see the sun. Another hypothesis was that it was just the matter falling into itself was creating a very strong gravitational field, and the gravitational field itself was the fuel. And if you go through those calculations, the sun lasts on the order of tens of millions of years. And even so, we know that that can't possibly be the answer.
Right. It doesn't line up with the evidence we have from
up.
radiometric dating.
And so it wasn't really until quantum mechanics was developed and we understood the processes of fusion and fission
to make an atom bomb.
Right. Well, shortly after we made an atom bomb, correct? Right. With uranium. Uranium fission? Is that what it is?
First, yeah, they used fission. Uranium at first, yeah. There was a fission bomb and a fusion bomb. One was uranium, one was plutonium. But that's a kind of interesting sort of experimental, like an empirical proof of that. It's sort of like we figured out what was going on in the sun, and we were more or less like, well, let's do it here.
Well, quite the opposite of that, actually.
Okay.
We were trying to figure out how atoms worked, and then whenever we had an idea of what fusion even is, the structure of like a nucleus being made up of like protons and neutrons and kind of how they interact and such. If we assume that the sun is made of hydrogen and it's under very high pressures and temperatures, it's undergoing fusion because those atoms are being forced very close to each other. In the fusion process, you bring a hydrogen atom and a hydrogen atom together, they make, well, you have to have 4 of them, and then they make a helium atom. In that process, a bit of energy will be released. And if you do that process a bunch, that bit of energy becomes quite a bit of energy. And whenever you do the calculations for that, it gives us a really an answer pretty close to what we expect the sun's life should be, and accounting for also why it's so bright, is the fusion process is the fuel that answers that question.
So we actually discovered fusion first, and then we were like,
Yes.
"Oh, okay, this is what's happening in the sun."
This must be what's happening in the sun, because it finally checked all those boxes, right? It's like we couldn't account all the fuel types we use. They were just like many orders of magnitude, like they would burn so quickly. There's
Yeah.
no we couldn't make an account for it until quantum mechanics came about, and we understood these fusion processes um, very well enough to create bombs with them.
Yeah. And nuclear power, something a little bit more handy.
Yes.
Wow, that's really cool. Yeah, it's crazy how all these lines of evidence sort of converged eventually. It took a long time. There was so much pushing and pulling, but we're kind of at this point where it's like everything's pointing to the same number, and that's kind of satisfying.
It is really nice.
When you're studying like the fossils and you're studying the rock formations and stuff, and your numbers are lining up with the guy in the lab calculating fusion, it's like, oh, well, that's cool.
Getting back to something I said earlier, I said the sun was a main sequence star, and this is sort of like where stars spend most of their time, is on the main sequence band. The stars in this band are what we call, they're at equilibrium. And so like the matter wants to go towards the center due to gravity. And then in the center, we have these fusion processes happening, which are emitting energy outwards. And nature just kind of does its thing where it becomes in this equilibrium of balance, where the inward force of gravity is pretty much equal to the outward force from the fusion. And that's what determines the size of your star, is essentially how much mass there is and how fast it's burning that fusion.
So right now it's at the stable state, and it's going to be at the state longer than any other state.
Right, so it's very early stages whenever it was what we call a protostar, and its fusion processes just happen, or were just happening. It wasn't quite dense enough. That was a very short stage of its life, and then whenever the fusion started to happen, whenever it got small enough and then those pressures and temperatures were high enough, it came into the main sequence stage, and it's been in that stage for billions of years at this point, and we expect it to stay for another few billion years before it turns into a red giant, and then it eventually will collapse into a white dwarf. However, the main sequence stage will last for, say, 10 billion years, on the order of something like that. The white dwarf will last for a very long time, because it'll just kind of be like a dead chunk of degenerate matter at that point. That's just like, it's not really fusing anything at that point. It's just like a hot object that's just kind of sitting there.
And we get this information, I guess, from observing other stars and seeing what's going on at their stage in development.
Right, looking at other. So we think it's going to be a white dwarf as the end stages of our sun, and so we go look out at other white dwarfs and kind of study their properties.
Now, I know a lot of stars, when they get to the end of their life, they blow up, they supernova.
True.
So why is the sun not going to supernova, and rather it's going to become a white dwarf?
Only the most massive of stars undergo supernova explosions.
Is it either or? Is it supernova or white dwarf, or is there any other?
Oh yeah, in some stars, so if it's not massive enough, it won't quite undergo fusion, and then we call that object like a brown dwarf. There are, so white dwarfs and neutron stars are stellar remnants of like, so neutron stars are stellar remnants of like supernova explosion. White dwarfs are remnants of stars that undergo a red giant phase, like ours will. And the most massive of stars, stellar remnants, will be a black hole. That's the types of stellar remnants that. And the black holes obviously only come from the most massive of stars, because you need quite a lot of mass in order to create that much pressure.
Interesting. Yeah, I didn't know that about supernovas before you told me. That's interesting. I just sort of assumed all stars went supernova.
Oh yeah, no, each but it really depends on your mass. The most massive of stars will undergo supernova, and supernova are, by the way, where we get our super heavy elements from.
Because now that was the next thing I was going to ask. So I've read a bit on like the early parts of the universe and stuff, and all our heavy elements were made inside the stars. Was the matter in our solar system made from the sun?
No. So in order to get our solar system, what we do is essentially we start with a gas cloud of hydrogen, essentially, maybe some other elements mixed in there. And if it gets to a point where the pressures become low enough or the temperatures become low enough, it'll start collapsing in on itself, and it'll slowly just all come together to a really small point, essentially. The lightest of material will all go towards the very center.
When you say lightest, do you mean like least dense, or like hydrogen and helium,
as
or what do you mean?
Elements?
Okay.
So hydrogen is your lightest element, and then a bit of helium, and that will go towards your sun, and you'll have what's called a protostar, where all that material is just kind of feeding into it. And then as the material collapses, the initial cloud will have a net rotation about it, just from like floating in space. It just kind of, and it might be a really slow net rotation, like meters per second on a cloud that's a half a light year across or whatever. But in order to conserve that angular momentum, as you go smaller, you have to spin faster and faster. Think of a ballerina whenever, or
like when you're spinning
skater.
Your chair.
Yeah. They put their arms out, and that's their mass distributed over a large area. And as they're spinning, when they bring their mass closer to their body, in order to conserve that angular momentum, you have to speed up.
Yeah.
Right. Same principle for building the star. The big cloud of material has some tiny amount of angular momentum associated to it. But as it gets closer and closer, it must speed up quite significantly in order to maintain the conservation of momentum.
Right.
And what happens is you get the angular momentum kind of like forms into this disk that rotates around the star, the protostar. And then that disk will form the planets that we have eventually, and then the star will just turn into the star. Well, the protostar will turn into the sun eventually.
In the early stage of the stars. But not our sun.
Right, not our. So the heavy elements are always made in the later part of stars.
Oh, okay. So our sun hasn't made any heavy elements because it's just not far enough in its development yet. That's
right, and it will later. Stop at iron. Iron is as heavy. You can't. Whenever you try and fuse iron, how I was saying earlier, if you take 4 hydrogens and make a helium out of it, it releases a bit of energy. In order to fuse hydrogen, you have to input energy. It doesn't release it anymore. And so the fusion process, keeping the star at that outward pressure I was talking about, eventually, whenever you get to iron, that outward pressure will go away, and then it'll just collapse in on itself.
Interesting.
And then that's how you get to the white dwarf.
So all the heavy elements we have in the solar system that the planets are made out of, those all came from a star that is already dead.
Mini stars.
Yes. That were already And then they're like long gone.
Long gone. Yep. Their stellar remnants might still be around. The dwarfs, white dwarfs they turned into, the neutron stars they turned into, but yeah, long gone.
That's so interesting.
We had to have many generations of stars kind of go through these processes. And well, the universe is it's had a long time to go through.
Yeah.
Lots of generations.
So did the sun itself also come from the remnants of other stars, or like
no,
how do
not.
we get a sun?
Well, we know the sun is mostly hydrogen, right?
Yeah.
And hydrogen is just given to us from the early Big Bang. Like it was just sitting out there.
It's just here.
Yeah.
we don't know where the hydrogen came from.
Yeah, we can't make an account for why the universe is here, aka the stuff in it.
Okay, but well, given that we have hydrogen, how do we get a sun?
It just collapses in on itself, and it gets really close and really close and really close, and eventually it just gets hot enough to burn, and then that's what we see is the sun from that.
So suns are just something that happen whenever you have hydrogen.
Yeah, if you have, so in order to create a star, we just start with a big cloud of dust, essentially, and regions of this cloud will collapse in on itself. Like you have this huge cloud, and then over here, a tiny bit will collapse in on itself, and that'll be
just
a star.
Like because of gravity, or?
Yeah, just because of gravity. So it's a gas, so it has certain properties to it, namely temperature and pressure. Right. And the temperatures can be, whenever the temperatures get quite low, and if the pressures are quite low, it'll be kind of a dense region. And then if you kind of just like fluctuate into kind of a dense region, you'll cause like a feedback loop where it'll start collapsing in on itself. And then so if you have like a huge giant cloud, you'll have just little pockets of it collapsing in on itself that meet those criterion of having certain pressures and temperatures needed in order to collapse. And then so in huge nebulae is what we call them, like star nurseries. And it's because they're like generating little bits of stars like over here and over there and such.
That's a weird concept to get my head around. Is just like the
scale
it's just
is
like a natural
different.
process. Yeah. I'm thinking of like a valley. Like a valley is just something that happens when you leave water and earth around, and eventually there's going to be a lowest point, and the water's going to go there, and after enough time you have the Grand Canyon.
Right, after a long time, yep, get something like the Grand Canyon.
But if you wait long enough, you get a sun. It's the right stuff.
Right.
That is so.
The right stuff is everywhere. There's so much hydrogen in the universe. Most of the universe is hydrogen. So yeah, there's a lot of fuel for stars, as it were.
Yeah. Are stars like the most common thing, I guess? If you're judging by mass, probably certainly.
Yeah. Because, I mean, yeah, stars. But there's more planets than stars, I guess you could say.
Like in terms of like number.
There would be way more planets than stars.
But not like when you do mass.
Oh, by mass. Yeah, because any solar system, most of the mass of that solar system will be in its star.
Right.
Yeah, but yeah, that has to be how that works.
So if you're like making an account of the universe in terms of mass, because individual objects is kind of tricky, because you can kind of keep breaking things down smaller and smaller.
But exactly. You have stars, and then you have planets around the stars, and then some of those planets have moons, and then those moons might even have smaller moons around them.
From a certain perspective, it makes an object like the Earth or Mars or something. It's almost like more novel than the sun in some sense, because.
Oh yes, I
mean?
think that's true. Yep.
But it's almost the opposite of what the first intuition, I guess, because like we're in the solar system with one sun and 8 planets. Sorry, Pluto.
Sorry. Yeah.
Rip. But the sun is kind of the status quo, and the planets are sort of the weird thing. It's interesting.
Mm-hmm. And our solar system is, from what I understand, pretty unique in and of itself, in that our giants are on the outskirts, sort of. They're like on the outside of the solar system. And our rocky planets are closer to the center. That's not normal. Normal.
It's certainly unintuitive to me because, gases are typically like hotter. So you think
Right.
closer to the sun, more gases, more gravity, larger.
Mm-hmm.
That is weird.
So, from my understanding, quite a lot of stars have gas giants like where our orbit would be,
Right.
a lot closer. But we're kind of flip flopped a little bit.
So this is a slight pivot, but we have a good amount of time still. So the sun is a common type of star, and it's in its most common state. And
Right,
we're
it's in
here.
its prime, as we
Yeah.
could say.
So we get into this thing of like, well, if there are a lot of suns, why are there not a lot of Earths? And you just kind of put this idea in my head where it's like, well, most stars
Mm-hmm.
have their gas giants closer to them. Is that perhaps one sort of explanation for why we don't see more Earth-like planets? Or
I think we don't see more Earth-like planets because they're hard to detect.
yeah,
I think that's what it is. I think whenever our instruments get better, I think they'll just start popping up everywhere. I mean, and they have been more or less.
Okay, so even though it's a little weird that we have,
Yeah,
our rocky
our
planets
solar system isn't like far from the status quo. It's just strange in that one little aspect. I mean, you can there's certainly many sun-like stars with Earth-like mass, and by Earth-like I mean Earth or like 5 times Earth. Not getting too crazy. But those kind of planets of those sizes around suns like our star, or stars like our sun, I expect to be, I mean, not unusual.
Yeah, I mean, even like on the scale of the universe, even unusual things are common.
Right.
Supernova are kind of rare, but you can see those
Right.
all the time, even if it's like a 1 in a trillion chance. Like
And we have
they're gonna be
200
lots of
trillion stars. Like, we'll
Yeah.
get there. Like, we'll get there.
That's an interesting thing you mentioned about them being pretty hard to detect. I recently read that Neil deGrasse Tyson astrophysics book, and he talked about how to detect another, because we can't. It's not like we can just take a telescope and look at another star and see the planets orbiting it. Like
No.
it's. He describes it as having to watch the star and wait for like a little flicker in like a certain field, and you can tell that there's an object of a certain size orbiting it, basically.
So, one tricky thing is if you look directly at a star and there is a planet orbiting it, as the planet gets between the star and us, the star will appear a bit dimmer. It won't completely block it out, but it'll just get a little bit dimmer, and then it'll get brighter again as the planet goes around it. So, that kind of detection for planets only works if the plane of that solar system is like exactly aligned with us. We have to see this the planet has to go in front of the star. It could be like around the star. It would never
like the
cross,
other way.
It would never cross the star in our field of view. And so we have to use other methods as well as that one whenever we can, in order to detect planets around stars.
One other thing you can do is look in other ways other than visible light.
Yes,
like
that's
perhaps
true.
Infrared light.
Which we will be able to do as soon as James-Webb, which is launching in December, 36 days.
Yeah.
Yep. James-Webb will be looking, from what I understand, James-Webb will be able to look at atmospheres of planets around other stars, which is kind of fascinating.
Yeah, it's really interesting because we're talking about luminosity, and like when you're looking at a far star, the star is super, super bright, so bright that you won't see the planet. But the infrared difference between a star and a planet actually isn't. It's still a big difference, but it's not as much.
So as the planet goes in front of the sun or the star, the light will kind of filter through its atmosphere, and in that process, the different types of elements in that planet's atmosphere will kind of filter out some of the light. And so from that, we can we know what the light from the star should look like, and then we see these little dips in light, or we say bands of light, where they kind of just like disappear. Like certain
Mm-hmm.
colors will just kind of disappear in small little discrete bands, and those little discrete bands correspond to different elements and or molecules, and then from that we can determine what kind of gas it must have flown through in order to get those bands, and then from that we tell the chemical composition of the gas, which is the planet's atmosphere.
So that will be exciting. One other note on infrared, again, this is only slightly related. Stars emit a lot of different rays. They emit visible light, but infrared, that's, am I correct? That's the warmth you feel from the sun. You are feeling the infrared.
Yes. Or the U. That's a good question. Most of the light of the sun is visible light.
Right.
And then the infrared. I don't know what's carrying most of the energy.
Yeah. Well, I know the heat energy.
Right.
I know you take a light bulb that's a normal light bulb. You put your hand over it and you feel the warmth, and the warmth you feel from that, I know, is infrared light, and you can see that by like putting on infrared goggles, and you can see the
Right. It'd be really
infrared
bright.
bands. Yeah.
Right.
But if you get an LED light, it puts all the energy into visible light, and it doesn't waste the energy on infrared light. And if you hold your hand up to one, it's not warm
it has
at all.
high intensity light, which
Yeah.
is very bright light, but the energy of light is not dependent on how bright it is.
Right.
It's dependent on other factors.
Which is cool.
Yeah. I think it's very quite strange, because like sound depends on the energy of sound is largely how loud it is.
Yeah.
Right. That kind of makes sense.
Could you have a star that's like cold or relatively cold?
Relatively cold compared
But
to like
still really
most other
bright?
stars? No.
Yeah.
So luminosity depends on two things: surface area and temperature.
But I thought we just established that it doesn't necessarily.
No, luminosity, the equation of luminosity is surface area times temperature. And so if you want higher luminosity, you can get a bigger surface area, or you can get a higher temperature. Or
The
some
luminosity of
combination
stars.
of anything.
Anything?
Anything.
Well, then how do you explain like a small bright LED light versus the less bright not LED light that's a lot hotter?
Okay, so this is the luminosity of like a black body, so nothing with input energy.
Oh, okay.
Right, so for a light, for instance, that we use at home, we're inputting electricity, and so
Right.
that's where the extra brightness comes, is from that.
Well, does it? Because LED lights use a lot less electricity than non-LED lights.
Right, but it's not a black body. It's still you still have to plug it in order to get the light, right?
Okay.
So yeah, it's still taking electricity from the house or whatever in order to shine.
Okay. But stars, you don't plug in stars to electricity.
No. Like even you or I, we're emitting light.
Yeah.
And
well, are we emitting it or are we just reflecting it?
No,
we're actually producing light.
You are producing light because you have a surface area and a temperature.
Oh, that is weird.
Yeah.
That makes sense. So like a very dim fire.
For my homework, I had to calculate what my luminosity was. It's very low.
That's so weird. So if you took like trillions of people and like put them in a ball, could you see them from like...
No, it would be very. It's still, yeah.
You need a truly massive amount.
Eventually, true. Because, like I said, it depends on two things: surface area and temperature. So if you get a big enough surface area, eventually it'll be pretty bright.
Oh, I did not know that. That is so strange. I mean, it makes sense, but it.
And so another thing. I'm leaving out a tiny detail. It's temperature raised to the 4th power. So a smaller increase in temperature will be a much bigger increase in luminosity, but it's just surface area, so you need a really large surface area in order to make that temperature gap, to make up for the temperature gap.
It sounds so not fascinating, but I've never
Oh, no,
thought
I
about how
think it is.
temperature, how luminosity is dependent on temperature and
Surface area.
area.
And that's it. And that's it, too.
Yeah.
Just those two things.
Like if you could force your body to heat up, like outside, not even like no fire or anything like that. If you could just make it hotter,
You would be a little bit more luminous.
and that makes sense.
Right.
I could imagine you just like standing on an oven and you just
so-
slowly turn red and like
Right.
light
So
up.
this makes exact sense whenever we think about let's go to our oven, right? Whenever
Yeah.
we turn on the thing, as it gets hotter, what happens?
It
starts emitting
yeah.
more and more light, and we see that red light coming out of it.
Yeah, and there's no. This is so weird. There's no light there. Oh my gosh. So it's already emitting light even before you heat it up. Actually, it's just
it was just light we can't see yet because it's
And
not.
so are we.
It's
Oh,
not
man.
within our visible range.
This is.
And that's why we see red first, because red is we can't see infrared, and then it gets into the red phase. And then if we kept heating the heating element even more, it would go to white hot, as we say. And then if you look at our HR diagram, the cooler stars are red, and then we have the white hot stars. And so like
I've never thought about it that way. I've never thought about how literally everything is emitting some amount of light. Oh wow.
Yes, if it has a temperature.
Yeah. Well, I mean, everything that's not
has
a single
yeah.
atom.
Yeah. Right, exactly.
A single molecule, yeah.
Right.
Oh wow.
Yeah. No, I share the fascination.
So this might sound kind of silly, but again, it's just the conclusion of this. It's the sun isn't bright because it's a burning ball of gas.
Right.
It's bright because it's hot and it's big.
Yep.
The fact that it's
That's
burning
why
is that's just an incidental fact about why it's hot, but it's not why it's.
That's why it's hot, but that's not how bright it is. Yep. Well, they're all kind of connected, right?
They're connected. They're connected. Yeah.
Right.
But like when you're just looking at the very specific details, like it's not a fire isn't bright because it's burning. It's bright because it's hot.
It's right because it's hot. Yeah, exactly.
That's not how I always just thought about it like, okay, there's a chemical process that produces light, and light is just like a chemical reaction, basically.
Right, exactly.
I never thought about it as being just like a fundamental property of every
just matter,
complex molecule or matter. Yeah, matter's
just matter in general. Yeah,
yeah.
It's just a property of matter that if it has a temperature, it emits light.
Well, I definitely learned something that makes me really happy, and you guys listening should let us know what you think and what other stuff you want to hear about astrophysics. We're going to be talking about everything from what'd you say, like galaxies and
galaxy clusters.
Yeah, maybe some other stellar objects too. Like, I mean, black holes is kind of a.
Oh no, that sounds super fun. Anybody who wants to learn about stars, look at the HR diagram, learn kind of what it means, and from that picture, you can learn an awful lot about the kind of stars in our galaxy and other galaxies and such. But anyways,
yeah, sweet.
Until next time.
See you guys.